All right, guys, welcome to Unit 3 Dynamics. We're continuing on in our study of dynamics, or forces. And so now we're going to start working in 2 dimensions. Everything up until now has been in 1 dimension. And so if we looked at that, we drew our free body diagrams. We had, call this force 1 acting this way and force 2 acting this way. So everything so far has been in 1 direction. So far, they all kind of look like this. Here's in the vertical direction. And what we've done is, remember, we've said the net force is mass times acceleration. And so what that means is if there's an imbalance somewhere, that means an acceleration must occur. And so that would be this guy right here, right? So as long as the net force is 0, there's no acceleration. If there is a net force, then the object does accelerate. So what happens in 2 dimensions? So a quick review in 1 dimension. If they're both pointing in the same direction, like these guys are right here, we know we add them up to get to 20. So it looks like they're going in what we would call the positive direction, okay, to the right. And over here, the second one here, we have 2 negative directions, or to the left, and so they would end up a net to the left. Well, what happens when we have a positive and a negative? It looks like we have a 0 Newton force here. And then we have the more interesting stuff right here. So we're going to look at this is what happens when we have things in multiple directions. So what we have here, let's call this A. And what's going on is we have to remember that we're adding things in triangles or using trig when we do this. So here we have a 10, and here we have a 10. And then what we're looking for is the net force, or this right here. And we get that by doing Pythagorean theorem. Oops. So in it, we go 10 squared plus 10 squared equals the 14.1 newtons. For B, it looks like the same thing happens, only we have a positive x direction and then a negative direction in the y, and we still get that 14.1 Newton number. All right. On the other side, we have this thing here. There's no numbers attached to it, but it's something we can kind of visualize. What happens here is both of these vertical components are pieces of the 10. Notice down here is that this 10 has a positive direction there and a negative direction there, giving me the result here, meaning there's no x direction. The x direction ended up canceling itself out, but I do have a y direction. And in this case, if we're assuming that these angles were the same, we would have chunks of that equaling 10. So what does that look like in terms of a problem? Well, what we have is a force here that is broken into its components. I'm getting my calculator here as we're talking. And first things first, when we do these components of things, we make sure our calculator is in degrees, right? We have to have our calculator in degrees. And what we have is an x component and a y component that we're going to start working with. So I'm going to look at this 100 Newton force here. I have something in the x and then something in the y. Well, if we remember our trig, it looks like I can use the cosine for the x chunk. So for this one, the x chunk would be, let me use the right color here. The x chunk here would be 100 cosine 30. Right, so when I do that 100 cosine 30, make sure my calculator's in degrees here. So 100 cosine of 30, I would get about 86.6 for the x direction. So this would be the 86.6 chunk there. And then for the y component, that vertical chunk, it looks like it would be 100 sine 30. So 100 sine of 30 would give me about 50. So those of us in pre-cal could hopefully would have seen that pretty quickly. So this is 50 for that chunk right there. Diagram B is pretty similar. It has an x component here and a y component here. We solve them the same way. Notice in this case, though, that my angle is 45 degrees, so those should be the same. Hopefully our math says they are, right? So for the x component, I have 100 sine 45. So 100 sine of 45 should give me 70.7. So this chunk is 70.7 here. And for the y component, it is 100 sine 45 also. Oops, I should have said cosine, my bad. But if you check on your calculator, 100 cosine 45 is actually the same thing. So shame on me. It should be cosine 45. This last one, we have the same idea. There's an x component and a y component. For the x chunk, it'll be 100 cosine 60. And for the 100 cosine 60, I get 50. And for the y component, I get 100 sine 60. And I get about 86.6. What's interesting is if we look at the y component of this one and the x component of this one, they're actually the same thing. They have the ratios of the side of the triangle. So that's kind of interesting, right? So all we're doing is building triangles again and using our trig functions to help us solve the question. Okay, so here's a pretty typical question you'll see in terms of some of the first questions we have. So we have a tow truck who's towing the car there. There's a force of 1,000 newtons on the vehicle, and it wants to know what is the vertical component that lifts the car off the ground. So what's actually happening here, right, and I think we can see that, is there is both a horizontal component, because it has to have one, and then a vertical component that's lifting it up. The vertical chunk is actually lifting it up. So when we look at that, okay, so we're going to look at the y component here, and it looks like it's going to be 1,000 sine 60. And so the y component of force is about 866.03 newtons. And so we'd say something like this, the vertical component is 866.03 newtons. All right, so that's how we would end up saying that or solving that little question there. Okay, so the last thing that we're going to look at is we're going to have these free body diagrams, and we're going to look at how we can manage them and figure out if things are moving or not. So one of the things that we want to look at, so this is an example of an object that is being pulled with some kind of friction, right? There's our mu there. But it's being pulled at an angle to the ground, and I think we're all pretty familiar with that, right? We have that normal force pointing up, we have the force of gravity pointing down, and then we have this force of friction pointing that way. And what we're going to basically be doing is we're going to figure out what or how we can simplify all this and work on the directions. And so what we'll do first is look at everything in the x direction. Okay, so I have the applied force is the thing happening at an angle here. Okay, so that's something to keep in mind. So I have the applied force in the x direction, right? That's going to be this guy right here. minus the friction force, and that's going to be equal to the mass of the object times the acceleration. And if we're assuming a zero acceleration, we just basically have to figure out what the x component is. So when we work on that, we have this 80 cosine 30 minus the friction force of 40 equals mass times acceleration. So we're trying to figure out if this thing is accelerating or not. Well, 80 cosine 30 turns out to be 69.3-ish minus 40 equals mass times acceleration. We need to know what the acceleration is, so all of a sudden I can go to my force of gravity equals mg, so 98 equals mass times 9.8. So if we see that, we should see pretty quickly that the mass here is 10 kilograms. So 69.3 minus 40 over my mass, which is 10 kilograms, gives me the acceleration of the object. So 69.3 minus 40 divided by 10. So we should get an acceleration of about 2.93 meters per second squared. In the y direction is kind of interesting what happens here. In the y direction, we can assume that it's not accelerating. So in the problems we're going to be working on, we're assuming it doesn't accelerate vertically for the moment. And I'll let you know when that does happen, right? So the applied force, remember, it has that y chunk we're going to be looking at. So everything going up minus everything going down should be equal to 0. Right? So up minus down equals 0. So I have the normal force, that's pointing up, plus the applied force in the y direction, minus the force of gravity, and that all should equal 0. So when I start plugging stuff in, the normal force looks like that's 58. The applied force in the y direction looks like it is 80 sine 30 minus 98. So 58 plus 80 sine 30 minus 98. So I end up getting 0 is equal to 0, which is what we hope for in terms of how we do these questions. So on this one right here, kind of have broken that down for us already. And so we're trying to figure out, is this object accelerating or not? And so what we're going to basically do is we're just going to look in the x direction and figure out what's going on here. Right? So positive in the x direction, I have the applied force in the x direction, that's this guy right here, minus the force of friction. And it doesn't look like there's anything else going on, so I'm going to say equals mass times acceleration. So pretty quickly, we should see that I need the mass of the object. Anytime we need the mass of the object, I automatically look at the force of gravity. Force of gravity equals mass times gravity. And it's given me some information here. It gives me 196 equals m times 9.8. We'll use 9.8 here. So 196 divided by 9.8 gives me a mass of 20 kilograms. So I'll write it in there just so it's easy to see. And what's going to happen is before I do any of the numbers, I look at this and all I'm really doing is this is the little equation I end up solving. And now I can just plug and chug. So f of x looks like it is 129.9 minus a friction force of 60. So it does look like there's an acceleration, I can already tell, divided by of about 3.0 0.495 meters per second squared. For this next one here, we have everything that is already broken down for us. And once again, we are looking to see how it's accelerating. And so once again, it looks like it's not going to accelerate in the y direction. So let's go ahead and do that one first this time. So let's see, net force in the y direction is 0. So I'll have the normal force going up plus the Fy going up minus gravity going down. And so it looks like the normal force is 174.3. The y direction is 70.7. And the gravity force is negative 245. So as you work through that, we should get 174.3 plus 70.7 minus 245. So we get 0 is equal to 0. So that's what we hoped for. And then in the x direction, right? Or I'm sorry, not 0. It should be mass times acceleration. So we have the Fx, this guy right here, minus the force of friction equal mass times acceleration. So the force of friction is 70.7. I'm sorry, the Fx is 70.7. The force of friction is 40 equals mass times acceleration. I need the mass, so I automatically jump to the gravitational force equals mg. So 245 equals m times 9.8. So 245 divided by 9.8 should give me a mass of 25 kilograms. So 70.7 minus 40 over 25 should give me the acceleration of the object. So 70.7 minus 40 divided by 25 gives me an acceleration of about 1.23 meters per second squared in the positive direction here. The last question we have will be these where you kind of have to fill in the blanks here. And so I know there's a mass of 10 kilograms, and the only thing I'm really given is the applied force. I know the force of gravity, so I'm going to start working on that one first. So I'll use purple here. So force of gravity is mass times gravity. If I know the mass is 10 kilograms, so Fg equals 10 times 9.8. So it looks like Fg is 98 newtons. So I know this guy right here, that's 98 newtons. Okay. In the y direction, remember, we've decided that for now, the net force in the y direction has to be 0. That means the normal force plus the applied force in the y direction minus Fg is going to be 0 also. And I can't just say now the normal force and gravitation are the same because there's a combination of things happening here, right? I have this extra applied force in the y direction. I need to be able to account for that somehow. And what happens is when I start filling stuff in, I have the normal force going up. The applied force in the y direction looks like it's going to be 60 sine 30. I know the Fg, that's 98. I just figured that out. So I can solve for the normal force. Looks like it ends up being 98 minus 60 sine 30. So the normal force looks like it is 68 newtons. So that's a little different from before where we will just set things equal to each other. Once again, there's this y component that I need to contend with. And once again, there's that x chunk that we need to look at also. All right, so there's that chunk there. I'm going to go ahead and look at whatever that Fx is. So it looks like that X component looks like it's going to be 60 cosine 30. So that looks like it is 52, estimating a little bit, newtons there. The friction force, that's not given right out to me, but friction force is mu times the normal force. And good thing I already found the normal force here. So it looks like I can just get my mu, which is 0.3, multiply it by my normal force, which is 68 newtons, and get a friction force of 20.4 newtons. So that's going to go right here. If I know that X chunk is 52 already, it looks like there's an imbalance between this guy and this guy here. So it looks like there is a net force in the X direction. So net force in the X direction is mass times acceleration. Looks like I have that applied in the X direction minus the friction force is equal to the mass times acceleration of the object. So it looks like that is 52 minus 20.4. The mass I already know is 10. So it looks like I can just subtract these guys here and get an acceleration of 3.16 meters per second squared. And the net force is just the mass times acceleration, and that should be 31.6 newtons. And so that, in a nutshell, is how you apply these application of forces in more than one direction. And this is kind of just the tip of the iceberg when we're looking at that. So let me know if you have any questions. Thanks for watching. Bye.